Hello everyone, welcome to our presentation at IROS 2024. Today I will be presenting our paper titled NeRF-enabled analysis through synthesis for ISAR imaging of small everyday objects with sparse and noisy ultra-wideband radar data. I'm Farhan, a PhD candidate at the University of Massachusetts Amherst. This work was done in collaboration with my colleagues Albert from Kitware, Professor Suren Jayasuriya from Arizona State University, and Professor Tauhidur Rahman, my advisor from University of California, San Diego. We will begin with a brief introduction to the challenges of ISAR imaging and contributions of our work. Then we will dive into the core of our proposal, analysis through synthesis optimization framework powered by Neural Radiance Fields. We will also explain the radar forward model geometry that is fundamental to our approach. Finally, we will showcase the results obtained through both simulations and real-world experiments and present an identification application of our method before concluding. There are a few key challenges in ISAR imaging, such as small objects result in low radar cross-section, making detection difficult. Radar resolution is often limited, affecting image quality. The imaging process typically requires complex and costly setups such as anechoic chambers. Limited measurements compromise effectiveness and reliability. Noise and motion artifacts can distort images, reducing accuracy. Addressing these challenges is essential for enhancing ISAR imaging techniques and their applications. The Neural Radiance Fields, originally designed for creating photorealistic 3D scenes from images, enhances inverse synthetic aperture radar imaging by addressing challenges such as resolution improvement, motion compensation, and clutter suppression. Techniques like ISAR NeRF, coherent, and CSR incoherent leverages neural radiance fields to reconstruct large targets, including satellites, buildings, and city maps, respectively. However, existing approaches mostly improve on already reconstructed SAR images for novel view synthesis rather than incorporating radar measurements as input signals themselves. We introduce an end-to-end analysis through synthesis optimization framework for inverse synthetic aperture radar imaging that leverages neural radiance fields that work in diverse conditions such as non-line of sight scenarios. Our radar forward model integrates ultra-wideband radar wave propagation and reflection characteristics. Our approach works without costly anechoic chambers or complex test setups, significantly reducing both cost and computation time. We show that our method outperforms conventional backprojection, especially in noisy environments, demonstrating robustness with limited views and sparse radar scans. In our hardware setup, we use a monostatic time domain ultra-wideband impulse radar P440 operating between 3.1 and 4.8 GHz. The radar is positioned at a fixed location in our setup. The object of interest is placed on a motorized turntable jacket to ensure steady rotational motion within the radar's field of view. We also demonstrate the feasibility of using a standard floor cleaning robot Roomba to collect data by integrating low-cost supplementary circuitry. In this slide, we'll present our end-to-end analysis through synthesis pipeline. In our setup, radar measurements are collected from N virtual radar positions, specifically from 360-degree positions that create a synthetic circular aperture. These measurements are then aggregated to form a 2D sinogram, where x-axis represents the range and the y-axis corresponds to the angle phi in degrees. After acquiring the sinogram, we sample the scene coordinates using a spherical sampling scheme based on the sensor positions. These sampled coordinates are then processed through a multi-resolution hash encoding block akin to instant NGP to generate positional embeddings. Next, the encoded coordinates are fed into our neural backprojection network module, a neural network consisting of 4 fully connected layers parameterized by weights theta BP. The network predicts the complex scattering function sigma for the estimated scene f theta v. These predicted scatterers are then used to generate radar measurements, that is, each scan in the sinogram, through our differentiable radar forward model. Training the network involves minimizing the loss between the synthesized measurement mf theta of v and the actual radar measurements y for each scan in the sinogram. In summary, our pipeline leverages neural network to predict scene scatterers and synthesizes radar measurements over time using a differentiable radar forward model. This slide illustrates our radar forward model geometry and sampling strategy. A transmitted ray in blue is emitted towards the scene, propagating through the scene chi, weighted by the directivity function Bt of x, and the transmitted probability Tot of xi. All transmitted rays within the antenna beam width, shown as orange lines, are sampled at the intersection points of the sphere defined by the range samples. Equation 1 denotes the received signal where L sigma is the scattered intensity. Equation 2 denotes the received ray where Li represents the depth samples along the ray calculated at ray sphere intersections. Transmission probability and between the transmitter, receiver, and the various scene point k are provided in equation 3, while equation 4 calculates Lambertian L sigma scattered intensity. Such formulations make the entire forward model differentiable. We encourage our audience to refer to our paper for more details about the radar forward model geometry. In this slide, we present the results of the synthetic data. We simulated 4 distinct synthetic scenarios, each containing single, double, triple, and quadruple point targets within the scene with added Gaussian noise per scan. As a baseline, we compare our method with time domain backprojection. To quantitatively evaluate our analysis through synthesis reconstruction against backprojection, we use 3 image metrics, namely peak signal to noise ratio or PSNR, learned perceptual image patch similarity or LPIPS, and mean squared error or MSE. The table on the left quantitatively compares these metrics, showing that analysis through synthesis consistently outperforms backprojection across all metrics in noisy scenes. The figure on the right represents the corresponding qualitative results. Analysis through synthesis demonstrates superior performance in noisy conditions. In contrast, backprojection shows significant artifacts around the corners of each reconstructed scene when noise is added. This slide illustrates the ISAR imaging results obtained with real data collected with a single cylindrical object within a cardboard box, 2 cylindrical objects placed at various distances apart, namely 7 inches and 27 inches, and a square metal container with a side length of 9.5 inches. The second and third column of the figure illustrate reconstructed images using backprojection and analysis through synthesis, respectively. Backprojection begins to exhibit artifacts as the complexity of the target scene increases. In contrast, analysis through synthesis reconstruction displays no artifacts and maintains the reconstructed target's dimensions more accurately to their original form. Now we present a real experiment video demonstrating the imaging of a soda can inside a cardboard box, showcasing non-line of sight application. The intermediate reconstructions are displayed at the middle bottom, while the final ISAR image is shown on the bottom right. We further demonstrate that even with sparse measurements, such as 30-degree skip angles, our ATS pipeline can reliably reconstruct the soda can inside the cardboard box. In this slide, we show applications of our proposed analysis through synthesis method for object identification. We enhance object recognition by integrating identification information into cylindrical containers and plastic helmets using 3D printed octahedral cornel reflectors. The top two rows show ISAR imaging of a cylindrical container with corner reflectors positioned at 90° and 180° orientations, while the bottom two rows display helmet with reflectors arranged at 120° intervals and in a linear alignment. The analysis through synthesis method effectively reconstructs the relative positions of the reflectors, whereas backprojection exhibits noticeable artifacts and fails to produce clear tag reconstructions even after a negative 30-degree dynamic range adjustments. This video demonstrates the imaging of the octahedral corner reflector attached to the helmet as identifiers, showcasing the object identification application of our method. The intermediate reconstructions are displayed at the bottom left, while the final ISAR image is shown on the bottom right. To conclude, we presented an inverse synthetic aperture radar imaging algorithm that uses an analysis through synthesis approach based on neural radiance field techniques. Our framework estimates scene scatterers via an implicit neural radiance field and optimizes with differentiable radar forward model, demonstrating significant improvements over traditional backprojection method in extensive experiments. This method eliminates the need of costly anechoic chambers, reducing both reconstruction time and cost, while enabling reconstruction in non-line of sight scenarios, such as imaging contents inside a cardboard box with sparse and noisy ultra-wideband data. Our ATS framework has diverse applications, including enhancing robot environment interaction through object scanning, reconstruction, aiding security screening by imaging concealed internal structures, enabling unlabeled warehouse package recognition without repackaging, and so on. Thank you for listening. We encourage the audience to refer to our paper for more details of our work.